So, welcome back. Hopefully you watched the first video, and believe it or not, I'm literally 10 minutes out after recording the first video. I'm just gonna record this one as well. So, if you watched the last video, you kind of just got the introduction, and we wrote down the formulas for what sine was in our Euler's notation and what cosine was in our Euler's notation. So, because the last video I proved, or I didn't really prove it, I kind of just showed you that they were equal to each other. In this video, I'm going to walk you through the integration in this formalism, right? And the reason for that is, as these integrals aren't hard to do, right? These are pretty easy to do. But what if we start getting into some more crazy ones, which we will do, and let's say you forgot your trigonometric formulas, right? If you forget your trigonometric formulas, these save the day, right? Because you can always integrate exponential functions, right? Integrating exponential functions are really simple as long as we don't get, out of, simple linear terms, which will never happen, right? And the reason for that is, for example, let's say you wanted to talk about, which we will do, but not in this video probably. Let's say you wanted to talk about the integral of cosine squared of x, right? And actually, I'll just walk through this one the normal way. The way you integrate this one is you must remember that cosine squared of x is simply equal to the square root of, I always forget this, is it plus or minus? I'm just going with plus. It's the cosine of 2x over 2, right? And only if you remember this can you integrate this, right? There is no other way you can actually integrate these ones. It's similar with sine squared of x. And see, and this is where I even get confused, because this might even be wrong. I don't have it off the top of my head right now, right? So this could actually be the opposite. This could be a minus, this could be a plus, right? And that's the issue, right? Sine of 2x, sine squared, I think you can do with some other formulas, but cosine squared, the only way you can integrate it is if you just happen to remember this. But what if you didn't remember it? Well, lucky for you, if you have this notation down, this is very easy to remember. And this will save you for all of them. You can actually write this. It's simply e to the ix plus e to the negative ix all over 2 squared, right? So in other words, we're just going to multiply these together. Right? And so if, of course, we have a FOIL here. So first, we're going to do e to the ix times e to the ix. And remember, we're over 2. So this is going to be, and we'll just put this all over 4 because they're all going to have it. So we're going to get e to the ix times e to the ix plus e to the ix times e to the negative ix. And we will simplify this in a second. I just want to write it out just so you can see all the algebra. And if you're probably at this point, some people have these formulas memorized. Some people know that a plus b squared is always a squared plus 2ab plus b squared. But of course, I'm trying our best not to have formulas written out. So if you have these memorized, you can go ahead and skip forward in the video. I'm going to do it slowly. E to the negative ix times e to the ix plus, finally, e to the ix, negative ix, is my bad, times e to the negative ix, right? Whoa, this looks pretty complicated, so let's simplify it down, right? Well, remember from our exponential algebra that if we have the same base, x to the a times x to the b is simply x to the a plus b. So we're just going to add these all together. So this first one, I get e to the 2ix. This one, I get e to the 0. This one I get e to the 0. And this one I get e to the negative 2ix all over 4. So, to save room, we're going to erase this guy over here, because that's just the long way of writing it out. And we're going to simplify this down, right? Remember, anything to the power of 0 is 1. So this and this become 1, and then 1 plus 1 is just 2, right? So we get 2 over here. So Now we can say cosine squared of x is e to the 2ix plus e to the negative 2ix plus 2 all over 4. And you can simplify this down in whatever way you want to. I'll just showcase some examples. We can say this is e to the 2ix plus e to the negative 2ix over 4 plus 1/2. Does it really help you? Not really, right? Because I'll showcase why. Okay. So now that we have this down, right? This, I'm not going to prove it. Just take it to be, you can prove it on your own if you want to do. You want to do some more exponential algebra, try it out with yourself. The way you would do it, I guess, okay, why not? I'll just go ahead and do it. Why not? So the way we would actually prove this is, and we'll just go ahead and integrate it. Okay, so we have cosine squared is equal to this. Now, we want to take the integral of this, right? Because remember, our whole goal of using this formalism is if I forget what the trigonometric form of these are, the trigonometric substitutions are. So let's go ahead and do this. I'll write this over here. Actually, I'll just do this now. So we're going to integrate it now. So let's take away all of this. And let's write up here because we want the most room we can get. E to the 2ix plus e to the negative 2ix plus 2. And what I'm going to do is, because remember, integrals have the property, and actually all linear operators have this property, same with derivatives. For example, if you have 4x, technically, because this is a linear operator, this is really, you can just take constants to go on the outside. This is actually just this, right? So this is a property of linear operators. I think so. I'm not a mathematician, so I'm just going to assume it's a property. If there's mathematicians in the comments, they're like, oh my God, Rami, it's actually not a property of all linear operators, blah, blah, blah. Who cares, right? We're going to say it has a property of linear operators and move on, okay? So a property of linear operators, and if you're like an analysis course, something like that, maybe don't take this to be a property of all linear operators. Or I guess it'd be more of a functional analysis course, not a real analysis course. So if you're in a functional analysis course, maybe this is not proof of all linear operators. But because this is a constant, technically this is 1/4 times all this junk, right? I can bring a constant on the outside of my linear operator. So this is actually just 1/4 times all of this, and we're integrating this with respect to the x. Now, I'm going to be pedantic, which means I'm going to do something I wouldn't do on an actual assignment, right? If this was for a homework or a test, I'm not going to be like, oh, a property of linear operators is that you can integrate all of these separately. But because this is for a video, I want to make sure, in case you forgot that from your course, a property of linear operators is that I can take these all individually, right? So this is equal to 1/4 on the outside times the integral of e to the 2ix with, and excuse my notation, right? Sometimes I'll forget a dx, but I'll try my best for the video, plus the integral of e to the negative 2ix plus, once again I forgot it, dx, of course, got to tell you what I'm integrating with respect to, plus the integral of 2, which technically is a constant, but we don't have time to really go back and fix that. Okay, so now let's go ahead and take the integrals, right? This first one, we are going to use a u substitution, right? We're going to say, and I guess this is where my different markers will come in handy. So I'll say for this first one, u is equal to 2ix, and du is equal to 2i dx. In other words, du over 2i is equal to dx. Now, the mathematicians that are very strict out there, an alarm will go off. They'll go, alert, alert, alert. Over here, you wrote a you wrote a rational number and you had a non-integer in your denominator. So that's more of like a historical thing. So for us, normal people, we're like, okay, I don't really care. I know how to handle that 2i in the denominator, right? But in order to be efficient, and this is a historical thing. Actually, I'll just talk about it real fast. So if in my view of the mathematical history, we have, some guy out there wrote out the what we call natural numbers, he said, well, there's 1 of something, there's 2 of something, there's 3 of something, there's 4 of something, blah, 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 right? Natural. Then someone came along and wrote out the concept of 0, right? And I don't really know who we want to attribute this concept of 0 to. I know there's some people who say the Indians did it. Some people say the Greeks did it. Some people say the Arabs did it. Some people say the Persians did it. I don't really care. I'm in 2021, so I know eventually the concept of 0 popped up, and we call these whole numbers. So we said, okay, well now I have the concept of almost no value, right? And then some businessmen came around and they said, well, how do I make sure if someone owes me something, I can keep this in my record? So eventually the numbers negative popped up, right? Just for that concept of debt. And I'm kidding, I don't really know if that's the historical perspective, but I would like to keep it that way. So notice there is no concept of I down here. There is no concept of I yet. There is no concept of square roots yet, right? So the next logical progression, though, is numbers between numbers, right? Someone eventually had to ask the question, this may have become in actual history, became before negative numbers, because we know there is a concept of breaking stuff in half, right? And if you break something in half, you get 1 part out of 2, right? But in order to keep this in mind for you to remember why you can't have I or square roots in denominators, look at the progression so far. We have no square roots. We have no imaginary numbers. So when you write the thing down of 1 over the square root of 2, we in the modern day can interpret this easily, right? However, mathematically, historic-wise, this makes no sense, because rational numbers were defined as integers, where A is an integer and B is an integer, right? And if you're not mathy out there, this just means in, and this is just the number for, this is just notation for integers, right? So if you write something as like 1 over root 2, this makes no sense. There is no root 2 historically. So mathematicians get their panties in a bunch. It's like, oh, you cannot write root 2 in the denominator. And that's fine. So because of that tangent, you're going to come over here. And now that you have the historic perspective, you're going to be like, okay, I will bow down to my ancestors. Thank you for laying down the work. So we need to get rid of this I in the denominator, right? So the first question is, what most people know from their algebra courses is, if I multiply both the numerator and the denominator by an I, this becomes I du all over 2I squared. Now, I squared, if you remember, I is defined to be the square root of -1, then I squared simply is -1. So down here, we erase this, write a -1, and this becomes I du over -2. So we can now throw this into my integral up here, right? So we will erase this over here. We will erase this over here because now we have the actual thing. And this is going to be I du over, and I'll put the negative right here just to put it out there, is equal to dx. And similarly for this one, and we won't go into the tangent for this one, we will say u is equal to -2ix, then du is equal to -2i dx. Therefore, because we can foresee that we're going to have to multiply by I, we can just do it right here, right? Let's just do it right here. So we're going to multiply both sides by I, and we're going to get I du is equal to 2 dx. Because remember, I'm getting an I squared here, which is -1. -1 times -2 is +2. Therefore, I du is over 2 is equal to dx. And so this method that we did right here, I think is more mathematically valid, because I don't even know if division is define to divide by I. We do it because, I'm not an actual mathematician. It's fine for us. So finally, we can go ahead and integrate this whole thing. So this is equal to the integral of 1/4 on the outside times, over here, we're going to substitute this in. So I get negative I over 2 on the outside of e to the u du plus, and okay, my notation's off, right? Because I shouldn't have used u over here and then put a plus eu. Some people might get confused and put 2u. We're not going to do that. We're going to use our color-coded to denote it. So over here, we're going to get I over 2 e to the u du plus the integral of 2 dx. Let's go ahead and integrate this. I get 1/4 times negative I over 2. Of course, we're going to get the integral of e to the u is simply e to the u. We're going to plug back in what we got. For u, it's going to be e to the 2ix. Over here, we have plus e, oops, I've got my constants. Don't forget your constants. We get I e over 2. Of course, e to the u, the integral of e to the u is simply e to the u. And because we know u is negative 2ix, we're going to get e to the negative 2ix. And then over here, lucky for us, it's a simple integral. We have integral, technically it's a linear operator. You take the 2 outside, you have integral of dx, which is just x, times 2. So we get plus 2x. So now I'm going to erase all of this junk over here because we're past that point. And we're going to distribute this 1/4 and simplify, right? Because remember, we want to put this back into our trigonometric notation, right? Because in this course, you're going to be expected to integrate cosine squared of x and get back a trigonometric answer. So finally, we're going to integrate this, distribute all of this through, and we are going to get negative I over 8 e to the 2ix plus, once again, over here we'll get I, positive I, over 8 e to the 2ix. And oops, I almost forgot the negative. That's very important, as we'll see, plus x over 2, right? Because 1/4, we get 2 over 4. Great. So now, this we'll leave alone. Oh yeah, and of course, I always forget, like I said in the first video, I'll forget this plus c from time to time. It really doesn't matter, okay? It really don't matter, right? Sure, if you have like initial conditions, all that stuff, it'll matter. If we're actually doing differential equations, we're not, so it don't matter. Anyways, so now we'll erase this, and we're gonna do some algebra on the side. What is e to the 2ix? We must ask ourselves. Well, remember, I'm going to arrange this with the 2x on the inside, right? So this is equal to I sine of 2x plus cosine of 2x, right? So then we're going to add another layer onto it. And then, of course, I should want to do this one too. EI to the negative 2x is equal to I sine. And remember, for the first video, sine is odd. So this negative becomes negative over here. And because cosine is even, the negative just gobbles up, goes away. So now let's add a layer onto it. Because you notice over here I have negative I and I. So now we're going to throw in an I on the outside here and I on the outside here. And I'm putting a negative for this one, right? So this becomes negative I squared. And then we have a minus I over here. And then this doesn't become negative I. Actually, I guess it does technically, right? Because we already had a negative here. So this becomes an I squared. And then this simply gobbles up an I. Okay. So now I'll put this in different color just so it showcases. So now this simply becomes, I'm going to factor out the 1/8 for now. So I'm going to keep this on the outside over here. This becomes this junk over here, right? So this negative I e to the 2ix, this one right here, and we're going to simplify this down. So I squared is negative 1, and negative 1 times negative 1 is simply 1. Negative I squared, this sums down to just 1. So now, this is the beauty of this notation, right? I have sine of 2x minus I sine of 2x plus sine of 2x plus I cosine of 2x, right? Now, and if this is not amazing, actually I made a mistake. This should be cosine over here, my bad. And if this is not amazing to you, I don't know what is, right? What we just noticed is this. This cosine and this go away, and I'm left with, oh, I wasn't green. And I'm left with 1/8 times 2 sine of 2x. Well, this is simply sine of 2x over 4 plus, and then I'm going to bring this guy down here, x over 2 plus c. So what did we just do? Without using any trigonometric substitution, we just saw that the integral of cosine squared of x with respect to x is equal to sine of 2x over 4 plus x over 2 plus c. And I believe if you look this up in any form, in any table, which I will do now, I'm not going to show it on my screen, but hopefully you can hear my typing. Let's see, integral of cosine squared of x is what? And we get 1/4 sine of 2x plus x over 2 plus c. So without using any trigonometric formula other than Euler's notation, you can integrate functions like this, right? And you can do this for sine cubed, cosine cubed. And as you can see, the algebra does get long, right? But, and for those, I guess we'll showcase a little bit. Those ones might be better handled with, your simple Pythagorean theorems. For example, sine cubed of x is equal to sine of x, cosine squared of x. And then here you can actually do a simple u sub of u equals cosine of x. Then du is equal to negative sine of x. And you can integrate those. So maybe for cubic ones, don't worry about it. But for even powered functions, maybe this might be worth it, right? But off the preliminary stuff, just, something, if you don't remember your formulas, this is the best way. The next video will showcase one with secant and cosecant. Hopefully this was useful.